previous lecture. Not a 1. Okay, so you all believe that the theory of weak interactions that I presented to you with a Lagrangian of the current form is correct. Yes?
So I'm a little puzzled by the weak interaction. So when we have neutrinos, only the right-handed ones, right-handed, left-handed, so only one kind interacts,
yes.
Right? Is there any better explanation for that than just saying, oh, the weak interaction does not couple to right? Like, is there any deeper?
Well, ultimately, no.
Just
But I'll try and make it a little more plausible today. So I guess what I'd like to say is there's no reason why the weak interactions have to couple to both the left-handed and right-handed parts of a fermion field, because they're two completely different fields. They could have different quantum numbers. So we'll talk today about the mass generation for fermions. And I hope that will make it clear that there's just no reason why the left-handed fermions and the right-handed fermions should have the same quantum numbers. If they don't have the same quantum numbers, they will have different interactions. So ultimately, what you want to understand is what is the pattern of quantum numbers of fermions in the world. Now, you remember that every time you have a right-handed fermion, its antiparticle is a left-handed fermion. So if you like, you could write all the fermions in the world as left-handed. So then I'd have a catalog that looks like this. The left-handed neutrino and electron, the left-handed positron, which would be the antiparticle of the right-handed electron, the left-handed quarks and the left-handed antiquarks. And so I have a big multiplet of fermions like that. And then I could just ask, well, what is the quantum number of each left-handed field? And the only reason for them to be symmetric, for the left and right to have the same quantum numbers, would be parity. But parity is broken. So that's not the right principle. We need another one. OK? So let's get a little deeper into it now. OK. Well, in the lecture last time, I wrote down this formula and the corresponding formula which included the weak neutral current. And we saw that the interaction was between vector operators. And certainly it's very suggestive when you write an interaction like that what's really going on underneath is that there's a vector that couples to a spin 1 particle, the so-called intermediate vector boson. And it's by integrating out that particle that I find this interaction. In order for that to work, this particle has to be a hard interaction. That is, it has to have a propagator, 1 over q squared minus m squared, such that for ordinary purposes, q squared is negligible with respect to m squared. That means that that vector particle has to have a mass. And so the first thing that we need in order to go further is to build a theory which allows vector particles to get a mass. Now, how do you do that? Well, I guess it's already been discussed in your quantum field theory course, I hope, that it's not so easy even to quantize the theory of the vector field. For a scalar field, what we do is we have operators ak and ak dagger. And then we have creation and annihilation operators. We can build the Fock space. For a vector field, the natural thing to do is to write an equation that looks like this. or maybe minus g mu nu. I'm not sure. We get in trouble either way, because the positive coefficient here has to do with the positive normalization of the states in the Fock space. G mu nu or minus g mu nu has indefinite sign. And if you write this equation, you necessarily get left over with states with negative metric, that is, negative probability. So, and this is a problem, by the way, for all higher spin fields, not just spin 1, but spin 3/2, spin 2, et cetera, et cetera. Eventually, it makes it really difficult to write consistent theories of higher spin fields. For example, the only consistent theory of spin 2 is gravity. So what can you do about that? Well, what you have to do is impose some kind of gauge symmetry in the theory in such a way that you can say the space components of A are real, and the time component we're going to gauge away. So it doesn't matter that there are negative probabilities in that sector. OK, but once you've written down a gauge theory, there are problems with mass generation. So to see that, let's write Maxwell's equations. And let me write this equation out in terms of A. So it's d mu of d mu A nu minus d nu A mu. And so we can write that equation as del squared of A mu minus d mu d nu of A mu is minus E J nu. Now I can choose a gauge. Let's say d lambda A lambda equal to 0. That would cause this term to go away. And then what I get is a massless wave equation with some source for A. It's a massless wave equation. There's no mass. That came directly from this equation, which is required by gauge invariance. If I wrote a mass term in terms of A, apparently that equation would not be gauge invariant. And I'd be back to where I started, namely the problem with interpreting this equation. So what can you do about that? It turns out that the solution to this problem came from the theory of superconductivity. And so for those of you who've been sitting in John Berlinski's lectures, the next couple steps are going to look very familiar. But if you haven't, you can just follow the equations. I hope it'll make sense. Let's write down a theory in which we take our abelian gauge theory and we couple it to a charged scalar field where d mu phi is d mu phi plus i.e. a mu phi. OK, now what I want to do is to, and maybe I should, without further ado, work out the current of phi in this theory. That is the thing that would appear on the right-hand side of this equation. So J mu is dl d a mu, right? Maybe 1 over E as well. That turns out to be minus I phi star d mu phi minus d mu phi star phi. And if I write that out, that's I d mu phi star phi minus phi d mu phi, like that. And then there's an extra term from this A piece here in the derivative. So that would be 2e squared. 2e squared phi star phi times a mu. Yes. Okay. So what I want to do now is take advantage of this structure in the following way. I'm going to add to this Lagrangian a potential, which depends on phi. I'm going to assume that that potential is such a form that I'm going to spontaneously break the symmetry associated with the gauge symmetry here, and then we'll see what happens. So let me write some symmetry breaking potential. For example, V is minus mu phi squared plus lambda phi to the fourth. So some potential that has a shape like that, and it has a minimum at phi is equal to V over the square root of 2. Now, phi is a field. If the potential is like this, the minimum is that value anywhere in space. Maybe I should say that this statement is actually a choice of gauge. Maybe I should write this statement a little better as I'm going to choose a vacuum in such a way that the vacuum expectation value of phi is uniform and it has the value V over the square root of 2. So in another gauge, remember, a gauge transformation of phi is that by gauge invariance, there's an equally good vacuum where the expectation of phi has this value times a phase, e to the I alpha x, where alpha is an arbitrary function of space, actually an arbitrary function of space and time. But I'm going to choose a gauge where phi is uniform. That's a very convenient thing to do. If I do that, then I can ask, what is the expectation value of the current in this vacuum? And now you see what happens. The expectation value of the current is, in this term, I have a derivative on the vacuum expectation value. So in this term, actually it's going to be 0 if I choose this particular gauge. Similarly here, I'm going to get 0 if I choose this particular gauge where phi is uniform. But from this term, I'll get something. And what I'll get is E squared times V squared times A mu in that gauge. OK, well, now we're cooking, because now I can substitute this into the equation that I wrote up there. And I get del squared plus E squared V squared times A mu is equal to 0. So I've now generated a mass for the vector field proportional to E squared V squared. In fact, the mass is E squared V squared. So that's pretty cool. The general rule is the following. If I have a symmetry in my theory, if the symmetry is gauged, but it's also spontaneously broken, then from the current associated with that symmetry, a term arises which is linear in A, and that term comes into the field equation for the vector field in just such a way that that vector field obtains a mass. This equation you may recognize from John's lectures. It's called the London equation in superconductivity. This phenomenon of mass generation in particle physics is called the Higgs mechanism. Yes?
Why did you put a 1 over E there?
Sorry?
Well, you first wrote J mu as the derivative of the Lagrangian.
Oh, I was a dummy, but I didn't take it. Oh, yes, I did. Let's see. I wanted to get this structure without the extra E in front, because I've already got an E here. And there shouldn't be an E here, but when I multiply by E, it comes back. I could do it either way. Okay. I mean, another way to see what's going on is just to take this Lagrangian and plug in the shifted form of the field. And maybe it's useful to do that. In fact, it's useful to do that to expose the field content of what I've done here. So what I've done is to say, so let me write this out as 1/2, if I integrate by parts here, a mu minus del squared g mu nu plus d mu d nu a nu plus some terms that involve plus d mu phi minus v of phi. Okay. Now, what I've done over here is to say the minimum of the potential is represented by expanding phi about some field configuration. Once again, I make the gauge choice that this field configuration is uniform in space. Now I can talk about fluctuations of phi about that field configuration. In general, this can be any function of x. However, I can use my gauge freedom. I can make a particular choice of gauge so that this object has no phase, so that the phase of this object is constant with respect to x. So I could write this expression as e to the I alpha, a general phi, as e to the I alpha times v over the square root of 2 plus, let me call it h of x, where h of x is a real scalar field, a real valued scalar field. I can then use my gauge freedom to gauge away this factor. And then let me plug this into this equation. So what's going to happen is the following. From here, I'm going to get, when I plug this in, I'm just going to get plus e squared v squared a mu squared. So that is the Lagrangian for a massive vector field. I'm also going to get a term from the kinetic energy terms, which is d mu h. Oh, maybe I needed a square root of 2 here. 1/2 d mu h squared. And from this term, if h is the minimum, you're not going to get a linear term in h, but you're going to get a mass term for h and some nonlinear interactions. There'll be some h cubed and some h to the 4th terms if you take the potential to be what I wrote over there. So the theory that I've written here, when you spontaneously break the symmetry, it has the following degrees of freedom. A massive vector field with mass E times V, E times the vacuum expectation value of the field, and one extra degree of freedom, which is this scalar field called H. So, as I've said, this mechanism for mass generation goes under the name of the Higgs mechanism. This mechanism was, yes?
Couldn't we have just written the equation for a massive vector? Lagrangian?
If you write this equation and you have a conserved vector current, that actually turns out to be consistent in an abelian gauge theory. However, in a non-abelian gauge theory, you run into all kinds of problems. There are extra ingredients that you need, and when you put them all in, you basically are going to get the whole structure out.
That's correct. Delta is squared plus m squared.
Yeah. You can't just add a delta a squared plus m squared to a non-abelian theory without running into, when you start computing diagrams, a non-conservation of probability. When you add everything you need to fix that up, you're back to the gauging. And if you like, in the abelian theory, it's the same thing. I could take this theory, and I could, as I were, integrate in to get back to here, and get a theory with totally equivalent properties. It doesn't make a big difference in the abelian theory, but in the non-abelian theory, you know, there are ghosts, there are extra interactions that you have. You need them all in order to have proper transformation. So this mechanism for mass generation of the vector field was proposed in the mid-60s by a whole group of people. Higgs, Kibble, Hagen, Guralnik and Kibble, and Broughton on Glare. The Higgs mechanism is kind of an abbreviation for that set of people. And there's something in sociology called Stigler's law, which says a scientific principle is never named after the person who discovered it. This law was enunciated by Mr. Stigler, who named it after himself as an illustration of that principle. And needless to say, this Higgs mechanism was, I think, really very well understood by Nambu years earlier. And before that, it came out of the theory of superconductivity, Bardeen, Cooper, Schrieffer. Anderson, I think, would add himself to that list. Yes?
This may be just a question I've heard asked, but is this the only way we know to give this vector field a mass?
Yes. In fact, you can. There are theorems that go the other way. Any theory, any renormalizable theory of a vector field must be a Young-Mills theory, either in toto or in disguise. It must have exactly the couplings of a Young-Mills theory.
Does unitarity come into that as well?
Yes. So you can look at unitarity, you can look at the high energy behavior of the theory, which eventually comes into the renormalizability. One way or the other, you need all the couplings of the Young-Mills theory. Now, as I said, in the abelian theory, the theory of the vector boson itself is a linear theory, so you have more freedom. In the non-abelian theory, you need the Young-Mills interaction to make everything work. Okay. So this is the Higgs mechanism in an abelian context. And maybe I should say there's lots more to say about this that I'm not going to get into. You can get a little introduction to it if you look in chapters 20 and 21 of my book. And I guess there are lots of other places to go. If you look in Weinberg's book, there's I think the whole literature is set out. But now I'd like to go up to another level. So far, we've only been talking about an abelian theory. But, oh, I'm sorry. There's one more thing I wanted to tell you about this, which is the counting of degrees of freedom. The original theory here, if I didn't spontaneously break the symmetry, I would have 4 physical degrees of freedom. Namely, the A field, which would be massless in that case, would have 2 degrees of freedom. Namely, the 2 degrees of freedom of a massless vector boson with transverse polarization. The phi field, being a charged scalar field, would have 2 degrees of freedom, namely the charged boson and its antiparticle. After the Higgs mechanism, we still have 4 degrees of freedom, namely the 3 degrees of freedom for a massive vector field. Remember that a vector field, you can bring it to its rest frame. It's spin 1. It has to have 3 polarization states in its rest frame, plus 1 degree of freedom, which is this field H. So somehow the charged scalar field has donated a degree of freedom to the vector boson, allowing it to become massive. I guess it's common to say that the vector boson eats a degree of freedom of H, and the degree of freedom that it eats is exactly the Goldstone boson, the massless particle that would otherwise result from spontaneous symmetry breaking. So the Goldstone so we have a situation with spontaneous symmetry breaking. I argued to you in last Thursday's lecture that that always leads to a massless particle, the Goldstone boson. However, through the Higgs mechanism, the Goldstone boson gets eaten, and it ends up as the extra polarization state of the massive vector field. We'll talk a little more about this in Thursday's lecture, I think. Okay, you had a question.
Pretty basic. Is phi or H the Higgs field?
H is the Higgs field. Well, it's both nomenclatures are used. Phi is called the Higgs field. H is also called the Higgs field. But the content, physical content, is just that there's one particle, which is created and destroyed by H, and that's the Higgs particle. Okay. Yes?
Is there any physical meaning to this expression of heat?
Eating? Yes, and we will discuss that on Thursday's lecture. I will try and make that very physical. Okay. Okay. So now we have the Higgs mechanism for an abelian theory. Let's now discuss the Higgs mechanism for a non-abelian theory. Here's an interesting example. Let me consider an Su2 Young-Mills theory with a scalar field in the isospin 1 representation of Su2 or O3, the vector representation. So here's the Lagrangian. F mu nu A squared plus d mu phi A squared. Phi is real, and A goes over 1, 2, 3, the three directions of space, minus v of phi. And what I'd like to do is to assume that we have a vacuum expectation value of the field phi. Phi we could think of as a vector in this fictitious three-dimensional space. So this is the same thing as SO3, rotations in 3 dimensions. So I have a three-dimensional space. If I have a vacuum expectation value for phi, let me write that as something that lines up in the 3 direction. In space, like that. And if it didn't line up that way, I could always choose the gauge in such a way that at every point in space, the orientation of phi is in the same direction. Okay, let's now plug this into here. So d mu phi A is d mu phi A plus G, and then what I need is the representation matrix. That turns out to be epsilon ABC, A mu B phi C. So that's actually the correct covariant derivative for something that's in the adjoint representation of the gauge group. The structure constant would appear here. Okay, so now we can write this as G epsilon AB3 A mu B times V. And if I just think of the field as constant, then this term goes away, and I just get the square of this term. So what I have for this, then, is 1/2 times G AB3 G AC3 A mu B A mu C V squared G squared. Okay. This is now getting interesting, because if I work this out, the square of an epsilon symbol, remember, is delta BC it's delta BC, delta 3,3, minus delta B3, delta C3, which is to say it's 1 when B equals C equals 1 and 2, but it's 0 when C equals 3. So the final Lagrangian that I get is something like this. The kinetic term for the gauge field, a mass term, but it's a mass term only for the fields 1 and 2, and not for the field 3. Equally well, I could write W plus is A1 plus I A2 over the square root of 2, and W minus is A1 minus I A2 over the square root of 2. And then this term here would be G squared V squared W plus W minus. It would be a mass term for a charged vector field. Yes?
Do you have to mix the fields to get a physical particle, or can you measure some particle just from one of the fields? Is there a physical particle that corresponds to the A field?
Well, I have to tell you how electric charge comes into this. But electric charge in this structure would be such that the W would destroy a positively charged particle, and this guy would create that electrically charged particle. So this is a very convenient way to write it. Okay, now what's happened here? Well, let's go back and look at this diagram. The gauge, oh, sorry, why don't you ask me the question? No, please. If you're confused, someone else is confused.
I was asking just where the Lagrangian is coming from, so
This one.
Yeah.
Okay, so this is just Young-Mills theory.
Okay.
Okay, this is a scalar field, and it's got to have a covariant derivative. So then the question is, what is that covariant derivative? So a covariant derivative is d mu phi is equal to d mu minus ig, a representation matrix, times phi. And then in the adjoint representation, that representation matrix is FABC. So for the rotation group, this is just epsilon ABC. And so that gives exactly this formula here, where G is the coupling constant. Yeah. So G is the charge, epsilon is the representation matrix, A is the A, and phi is the phi. Okay. Good. Okay. And this structure is always linear in A and linear in phi. So if you give phi an expectation value, you get something linear in A. When you square it, you get a mass term for A. That's the secret. Okay, now over here we had our whole set of rotations being gauge transformations of this theory. In principle, there are three distinct gauge transformations. One which is a rotation around the 3-axis, one which is a rotation around the 1-axis, and one which is a rotation around the 2-axis. If we have spontaneous braking, that is, if something sits down along the 3-axis and chooses that direction, this symmetry is spontaneously broken. This symmetry is spontaneously broken. But this symmetry here is not spontaneously broken. So in a very cool way, the theory actually understands that. This symmetry corresponds to an unbroken gauge symmetry. And so the corresponding vector boson A3 remains massless. These two symmetries are broken, so the corresponding vector bosons get mass. Then, maybe just to clarify Sean's question, this symmetry here is a U1, so we can identify that with electromagnetism. And then the J3 equals +1 state, which is exactly this state, would have positive charge. And the J3 equals -1 state, this state would have negative charge. Okay? So then, actually, this is pretty cool. We have a unified theory of weak and electromagnetic interactions. The A3 here becomes the photon, these guys are some massive bosons, W plus and W minus, which have electric charges +1 and -1. And they're of exactly the right form to mediate the current-current interaction. Actually, with one problem, which is that we needed another boson to mediate this part, the neutral current interaction, which is not there. So this thing is called the Georgi-Glashow model. It's a very beautiful model. It's perhaps the most unified theory of weak and electromagnetic interactions. But unfortunately, there's no neutral current. This term is not there. So what that means is that it's totally wrong. And we have to write down some other theory. Yes? Sorry?
It's the best that we have.
It's the most unified. It's totally unified, right? All three bosons come out of a single compact group. And that certainly seems to be better than any other choice. But experimentally, it's totally unified. Okay? Okay, so now that I've told you the wrong theory, maybe I need to tell you the right theory. And so let's try it like this. So the right theory was written down by Glashow a long time before the Georgi-Glashow paper. And then after Higgs and his colleagues came through and did their work, Weinberg and Salam made an improved version of this theory, which actually is now theoretically unimpeached. The theory is based on the symmetry Su2 cross U1. So this is the Glashow-Weinberg-Salam model. The theory is based on the symmetry group Su2 cross U1. And the basic thing that has spontaneous symmetry breaking is a field phi, which has the quantum numbers of a doublet of Su2, and it has charge 1/2 under the U1 symmetry. And because there are two different gauge groups here, which are independent and commuting with each other, we can assign two different coupling constants, G and G prime, and I'm going to do that. So then the covariant derivative acting on phi, as I said, this has the general form d mu minus IG, a representation matrix, A mu, and the field itself. This is going to be d mu phi minus IG, A mu A, sigma A over 2. So this is a representation matrix of Su2. Minus I G prime and 1/2, and I'll call the U1 field B mu. And all of that acts on phi. Yes? Sorry?
Phi, the very first term.
Yes.
Sorry, 2 what of SU2?
A doublet of Su2, a spin 1/2 representation of Su2. Okay. So now Su2 transformations will mix up all 4 components of this field. This field, by the way, is, I'm going to call again the Higgs field. Su2 transformations will mix up all 4 components of that field. So it's a perfectly consistent choice and also very convenient to say the vacuum expectation value of phi is equal to something in this form. Actually, more generally, I could expand phi as an Su2 matrix acting on the vector v plus h of x. Please notice there are 4 degrees of freedom in here. there are 3 parameters of the rotation group. So there's one more field left over. So once again, in this case, we'll get left over one real scalar field. OK, let's take this expression and plug it into here, or rather into the square of this expression. So we get d mu phi is equal to this acting on that is 0 minus ig a mu a sigma a over 2 times 0 v and then minus ig prime times a half times 0 v. If I now square this, then I get the following thing. First of all, for the components 1 and 2, this guy will be raised up to the upper component, and then I'll get an expression for the upper component of this 2-component matrix. And that will give GA1 squared plus GA2 squared times V squared. There's a half there. And that'll come squared. So when I square this vector, the upper components will give this expression. The lower component will give something a little more complicated. GA3 let's see. Sigma 3 acting on the lower component gives a minus sign. And then from here, there should have been a b mu here, plus g prime b mu, and there's a 2, and that comes squared, and b squared. So in the end, what we get are some masses that are g squared v squared over 4, but some other masses that are different. And I'd like to write out the eigenstates now that will diagonalize this. First of all, this structure is just what we found in the Georgi-Glashow model. So let's go to electric charge eigenstates by writing this. Actually, I think you have to do it the other way around, because these are the fields that destroy charge. And then this term here will turn into W plus W minus times the mass of the W squared, where MW is equal to G squared V squared over 4. Then this thing will be a single massive neutral field. So let me write Z mu is, let me get all the signs right. Sorry. Here we go. GA3 minus G prime B over the square root of G squared plus G prime squared, so the kinetic energy term will be normalized correctly. And there's a fourth field, which is the other linear combination here, namely G prime A3 plus GB over that same square root. And then I'll get a mass for the Z field which will be, I need to take out this square now, g squared plus g prime squared times v squared over 4. And then this field that's orthogonal to this linear combination won't appear at all. So the mass of the A field is equal to 0. So now we get an interesting theory. It's not as unified as the one before because there are two commuting gauge groups and two independent coupling constants. But what we get is a set of charged vector fields with the mass mw, a neutral vector field with a slightly higher mass, and then a fourth vector field which remains massless. Yes?
So this term with the W plus W minus and the Z field, what is it equal to?
Sorry? What is it equal to?
Yeah, there's an equal, but is it the covariant derivative of the Lagrangian?
Oh, so I'm working from here.
Okay.
So this term here is this term. This term here is this term. And there isn't anything else. We're done. So it must be that the last field stays at 0. Okay.
Another question?
Yes.
I just want a clarification about what exactly is different between you developing this theory and the one before. We just use a Higgs field here that is a spin 1/2 spin around your SU2
That's right.
as opposed to a scalar in the other theory.
That's right. And also we have an extra U1. Okay. So what's going to happen is that this expectation value would completely break SU2. The vector only breaks 2 generators of SU2. This one completely breaks SU2. However, it only breaks 3 symmetries. So there's one combination of SU2 and U1 left over. It's pretty clear what that is. It's exactly the symmetry. I should write this where you can see it. Goes to 1 down here and e to the I beta up here. Okay, that symmetry is still preserved by this vacuum expectation value. Yes?
What exactly do you mean when you say spin half? It's not real spin.
It's not real spin. It's a transformation on some internal space, but it has the structure of the rotation group in 3 dimensions. So whenever I have an SU2 group, I could classify the representations by spin. Maybe that's a little more familiar than saying doublet, triplet. If you have an abstract group, like SU3, you say the representations are a 3, an 8, a 10, etc. For SU2, we could say the same thing. The representations are a 1, a 2, a 3, a 4. But maybe it's a little, for some people, it's a little easier to think about it if you say spin 0, spin 1/2, spin 1. But it's not real spin. It's taking place in this internal.
So is it then because we're working in 2-dimensional representations of SU2 and U1, we write it as spinners?
Yes, the 2-dimensional representation of SU2 is exactly the spinner.
Okay.
Okay.
Can we then think of the components of those spinners as the different fields, or?
Yes. As I even indicated here, we'll think of this guy as a field with electric charge plus, and this guy as a field with electric charge minus.
So these three quantum numbers, I guess SE2 and U1, what are they called? They have names.
I'm sorry. Isospin and hypercharge. And this isospin is just to confuse you. It's not the same thing as the isospin we were talking about on data. So it's highly unilluminated. Okay. Good. Well, now we are slowly making progress toward understanding what the content of this theory is. I'd just like to introduce one more definition, and that definition will now allow us to connect to the stuff that we were doing at the very end of the lecture on Friday. Let me define an angle by the statement that tangent of theta w is equal to g prime over g. G and g prime are two arbitrary numbers. They're two coupling constants that are not related to each other. I had to introduce them as parameters in the theory. It's very convenient to parameterize their ratio in terms of an angle, which is defined in this way. Then the sine of this angle is g prime over the square root of g squared plus g prime squared. And the cosine of this angle is g over the square root of g squared plus g prime squared. And these sines and cosines are exactly what appear in this formula. So this angle is called the weak mixing angle, or theta w. So now what I'd like to do is to take the covariant derivative and work it out in terms of the physical mass eigenstate vector fields. So now let's say I have some fermion. In relation to the answer I gave to your question a little earlier, I can take a left-handed fermion. I could take a Dirac fermion, but I don't have to take a Dirac fermion because the left-handed and right-handed pieces, as long as I don't have any mass terms yet, don't talk to each other. So I could take a left-handed fermion, and I could put that in a general representation of Su2 and U1. And so let me write that here. The covariant derivative on psi would then be d mu minus ig a mu a, and then I would have here a generator of Su2, and then minus ig prime b, and then I could put a general charge under U1, and I'm going to call that charge y, the hypercharge. And in general, I can be in any representation of Su2, and y can be any number that represents the charge of that field. Now, please.
Can you explain how the concept of degrees of freedom works for this case?
Yes. There are 4 degrees of freedom in here. And then I have 4, let's go over here. So I have a mu a and b mu plus phi and phi star. So this is 4 times 2 degrees of freedom. 2 because these are massless vector fields, and there are 4 of them. And here I have 4 degrees of freedom because I have 2 complex scalar fields. At the end of the day, I have 3 massive vector fields, 1 massless vector field, and 1 field H left over. So that's 8. Sorry. That's 12, and this is 12, and it all works. Okay. Good. Okay. Let me now take this expression and try and reduce that in terms of the mass eigenstates. So it looks like this. For I, that would be sigma over 2 if it's in a spin a half representation. And if it's in a spin 0 representation, that just wouldn't be there. So what I have to do, so if I take these linear combinations, this becomes W plus sigma plus, and there's an extra square root of 2 left over, plus W minus sigma minus. And these terms are there if the field has isospin a half, if it's in a doublet. Then here, for the third component, I get something like minus IG, and A mu, as you can see from these expressions, is the cosine of theta W times Z plus the sine of theta W times A. And that gets a Z, yeah, that's right, times I3. Minus IG prime times the minus the sine of theta W times Z plus the cosine of theta W times A times Y. And the G I can write as G squared plus G prime squared to the 1/2 times the cosine of theta W, using the formula over there. And G prime is the same thing times the sine of theta W. So now I can simplify this expression in the following way. So first of all, I have something that can move me around in the doublet, namely sigma plus and sigma minus, if the field is assigned isospin 1. And so this field then will raise the lower component to the upper component if I put things in doublets or vice versa. The Z coupling is minus I G squared plus G prime squared times it's cosine squared times I3 plus sine squared times Y. It's very useful to write that in the following way. Cosine squared theta W times I3 plus sine squared theta W, sorry, minus sine squared theta W times Y is equal to I3 minus sine squared theta W I3 plus Y. So let me write that here. And I'm going to abbreviate sine squared theta W as just simply SW squared. It's just a number anyway. It doesn't matter what it is. Here I put I3 plus Y times Z mu. And now finally the A field has a coefficient cosine sine times I3 and sine cosine times Y. So that all factors out. So that'll be minus sine theta cosine theta times the square root of G squared plus G prime squared times I3 plus Y times A mu. And then this whole thing acts on whatever matter field I have here. Okay, so now I'd like to give this some kind of physical interpretation by telling you what reasonable matter fields are and what their quantum numbers are. But first of all, let me do one thing. The A field, remember, is the field that's massless. So that's the thing we would like to associate with a massless vector field that appears in nature. The one that we know about is the photon. The thing that stands in front of A is E times the electric charge. And so it's natural then to write E is equal to whatever that will turn out to be. G prime over the square root of G squared plus G prime squared is what it works out to be. And the electric charge is I3 plus Y. Notice that Q also appears here. And now I can write a rather simple form for this Lagrangian. So first of all, something that raises and lowers within a doublet, provided that the thing has isospin a half. Then a coupling to the electric charge, and finally a coupling to the Z, which, let's just write it like this. Z mu times I3 minus SW squared times Y times Q. And all of that acts on any field. Okay. So now how would I actually apply this to make a theory of the standard model? Well, now all I have to do is write all of the left or right-handed quark and lepton fields and assign them quantum numbers under these symmetries. So, please.
All right. What is so Z is the neutral weak boson.
Right.
What does it couple to?
It couples to everything that has either isospin or electric charge.
Do we know what it is, like, in nature?
Well, I'm just going to tell you right now.
Oh, okay. Sorry. Never mind.
So for the leptons, we have, let me assign the left-handed leptons to be in a doublet. Let me assign the right-handed lepton to be in a singlet. I know what the electric charges are, so I have to assign this y equals minus a half. So this one has I3 equals a half, y equals minus a half. It's neutral. And this one is negatively charged. This one here, I have to assign y equals minus 1. For up and down, I could put the left-handed states in a doublet. I have to assign them a funny value, y equals a sixth, in order to get the right charges of 2/3 and minus a third. And then upright and downright, I'm going to put in singlets. Don't ask me why I'm doing this. It's just what I need to do. Okay? And then what you see is that this term here is going to generate a current of the form up bar gamma mu down left plus nu bar gamma mu e, only the left-handed parts of the field. So that's exactly what we needed for the J plus current that I wrote down last time. And then there's a neutral current, which is mediated by the Z particle, which has every field with the quantum number I3 minus SW squared times Q. So for example, it'll have the left-handed neutrino with a quantum number a half. It'll have the left-handed electron with a quantum number a half minus SW squared, or rather minus a half plus SW squared. And it will also have the right-handed electron with the quantum number just plus SW squared. And let me call this J mu 3 Z. Okay, now what do I get when I integrate out these fields? Well, what I get is the following. I get some kind of effective Lagrangian, which would be two currents and a 1 over m squared, where m is the mass of the W and the Z. So I'll get g squared over, there was that 1 over the square root of 2. That becomes a 2 times mw squared times j mu plus j mu minus plus g squared plus g prime squared over mz squared. That same factor of 2 appears, yeah, times j mu z3, j mu z, I should have written here, squared, where this guy here is the current of left-handed isospin minus SW squared times the electric charge current. Exactly what I said was the thing that explains the neutral current interactions that we see in neutrino physics. We also have the relation that mw squared is equal to g squared plus g prime squared is g squared v squared over 4, and mz squared is equal to g squared plus g prime squared v squared over 4. So the ratio of these two is exactly the ratio of what's in the numerator. And we can now write the whole thing in the form that I wrote it last time. G Fermi times j plus j minus plus jz squared. So this was the thing that I postulated in the previous lecture. Now we've derived it in its complete structure from the SU2 cross U1 theory. We've introduced new charged vector bosons, which we gave mass through the Higgs mechanism. Also a neutral vector boson, which we gave mass through the Higgs mechanism. The fact that these coefficients are equal is actually a mass relation. mw over mz is equal to cosine theta w. And remember that the z includes this parameter, which is the sine of theta w. So there are all kinds of interrelations now between the electric charge, the mass of the w, sine theta w, and cosine theta w, which in principle could be falsified experimentally. And so what I really need to do now is to discuss for you how you would test this theory and whether everything is actually consistent with experiment. And that'll be the topic of tomorrow's lecture. Okay? See you tomorrow. Yes?
Fermions, like where do they?
Oh, I didn't get there yet. I'll discuss that on Wednesday. Yes?
So correct me if I'm wrong, but the fact that the neutrinos are left-handed,
we just put it in. Yes, yes. It's exactly here, because I'm allowed to put the left and right-handed species in different representations. So I'm just going to do that. But the reason that I want to do that is what I explained to you last Friday, that the weak interactions only couple to the left-handed species, as we know from these very detailed experiments on mu decay and neutrino scattering. So I'm forced to do this by the experimental results. Okay, good. Other questions? Good. See you tomorrow.